There is a place on Earth that has never been truly seen, not because we have not tried, but because the planet itself seems to resist us. At the top of the world, beneath ice so thick it bends the land below it, lies a region buried under glaciers older than human history. Despite all our technology and machines, we still cannot reach what lies beneath. In the Arctic, sensors fail, equipment disappears, ice closes over anything we try to lower into its depths. The deeper we push, the more the environment pushes back, as if the ice itself is unwilling to let anything pass. And yet, beneath all that frozen weight, there is a world, dark, immense, possibly alive. So settle in and slow your thoughts, because tonight we are drifting into the darkness beneath the ice and into one of the last great mysteries on Earth. The top of our planet is a strange kind of frontier. It's not a mountain to climb or an ocean to sail. It's a place that doesn't so much stand before us as hang over us, hidden under hundreds, sometimes thousands of meters of ice. When most people think of the North Pole, they picture an endless sheet of white stretching to the horizon. A featureless plain interrupted only by the occasional bear or expedition flag. But that's only the surface. Beneath that frozen desert lies a landscape we barely understand. Rivers that flow without ever touching the air. Lakes sealed off from the sun for longer than our species has existed. And perhaps even ecosystems that evolved in total isolation, cut off from the rest of the planet by a barrier of crushing, shifting, frozen weight. It's not just that we haven't explored it fully. It's that we can't. Not yet. Maybe not ever. The Arctic doesn't just resist intrusion. It erases our attempts. Machines break in ways we don't expect. Sensors fail under pressures we can barely imagine. Ice closes over anything we try to lower into its depths, sealing the wounds we make as if we were never there. The deeper we go, the more the environment seems to push back. And yet, that's exactly why this mystery is so irresistible. Because somewhere under all that ice is a world that's part Earth, part alien planet, and we're desperate to know what it's hiding. To understand why it's so hard to reach, you first have to understand what we're trying to reach. Glaciers are not just frozen water sitting in one place. They're dynamic systems, rivers of ice that move and shift under their own immense weight. The glaciers around the North Pole are among the oldest and most powerful on Earth. Some are more than 2 million years old, layered and compacted over countless freeze-thaw cycles. Imagine snow falling year after year, century after century, never fully melting, pressing down on the layers beneath it until they fuse into solid ice. Over thousands of years, that ice thickens, deepens, and begins to flow outward under its own colossal weight. That's what a glacier is, a slow, unstoppable river of ice grinding its way across the land, reshaping the earth beneath it. And these rivers aren't just thick, they're vast. The ice covering the Arctic Ocean and the Greenland ice sheet nearby can reach depths of over 3 kilometers. That's like stacking 3 Eiffel Towers on top of each other and still not breaking through. It's not a frozen pond we're dealing with, it's a frozen continent, pressing down with unimaginable force. Picture what happens beneath that much ice. The weight is so intense that it crushes the landscape below, carving out deep valleys, subglacial basins, and hidden channels where meltwater can flow. In some places, the pressure from above generates enough heat to melt the bottom layer of ice, even though the temperature remains well below freezing. That meltwater forms rivers and lakes beneath the glacier, sealed, away from the surface world. These are not the kinds of lakes you'd take a boat across. They're pitch black, oxygen poor, cut off from sunlight by kilometers of ice. And yet, some of them might have existed, undisturbed, for hundreds of thousands of years. Scientists know this because we've studied similar environments in Antarctica. Lake Vostok, for instance, a massive body of water buried beneath 4 kilometers of ice, untouched for perhaps 15 million years. The Arctic almost certainly hides its own equivalents, but they remain invisible to us. Radar can hint at their presence. Satellite measurements can detect the slightest bulges and flows in the ice above. But to truly study them, to see them, sample them, understand them, we'd have to get there, and that's where the problems begin. Drilling through kilometers of moving ice isn't just hard, it's one of the most difficult engineering challenges humanity has ever attempted. Ice isn't uniform. It's layered, riddled with bubbles, fractured, and constantly shifting. The deeper you go, the more the pressure increases, and the more the ice behaves like a viscous fluid, flowing slowly around anything you try to insert into it. Traditional drilling rigs, the kind used to reach oil or geothermal energy, aren't built for this. They rely on stable ground, not a constantly deforming block of frozen water. Even specialized thermal drills, which melt their way downward, face enormous challenges. As they descend, the ice can refreeze behind them, sealing the shaft. The deeper they go, the harder it becomes to maintain a stable borehole. And even if you reach the bottom, there's another challenge waiting. Contamination. The ecosystems beneath the ice, if they exist, have been isolated for perhaps hundreds of thousands or even millions of years. A single trace of modern bacteria introduced by a drill could destroy them before we ever study them. So scientists must sterilize every component, every drop of fluid, every instrument that enters the ice. That's slow, expensive, and incredibly delicate work. And under Arctic conditions, it becomes even harder. The Arctic environment itself adds another layer of complexity. Unlike Antarctica, where much of the ice sits atop land, the North Pole is covered by sea ice floating on an ocean. That ice isn't anchored, it drifts, cracks, and shifts constantly under the influence of winds and currents. A drilling platform that's perfectly positioned one day might drift kilometers off target the next. Equipment anchored in the ice can be torn apart by pressure ridges, massive walls of buckled ice that form without warning. Even the logistics of operating in such a remote, hostile environment are daunting. Temperatures plunge below -40 degrees Celsius. Winds can exceed 100 kilometers per hour, and polar night can last for months, cutting off solar power and plunging the region into total darkness. Every piece of equipment must be built to survive these extremes. Every mission must plan for them, and every mistake can be catastrophic. You might wonder why we can't simply send a submarine under the ice and explore from below. After all, nuclear submarines have crossed beneath the Arctic ice cap many times, but they haven't gone beneath the glaciers themselves. The reason is simple. Submarines are built for open water, not for navigating the chaotic labyrinth that exists under glacial shelves. Beneath a glacier, the interface between ice and rock, or ice and water, is irregular and constantly changing. Caverns form and collapse, channels twist unpredictably. Ice extends downward in jagged ridges, called keels, some plunging hundreds of meters below the surface. Even the most advanced submarines can't risk navigating such terrain without detailed maps, and those maps don't exist because we haven't been able to go there. It's a perfect paradox. We can't map the under-ice world because we can't get there, and we can't get there because we haven't mapped it. Robotic probes might seem like a solution, and in some ways they are. Scientists are developing autonomous underwater vehicles, AUVs, capable of navigating beneath ice, mapping the seafloor, and collecting data. These robots can go places humans can't, slip through narrow passages, and operate without direct control. But even they face severe limitations. Communication through thick ice is nearly impossible. Radio waves don't penetrate it well, and acoustic signals degrade quickly. That means once a robot goes beneath the ice, it's largely on its own. If it gets stuck, damaged, or lost, there's little we can do. Battery life is another major constraint. Operating in freezing temperatures drains power quickly, and there's no way to recharge deep beneath the ice. Most current AUVs can only operate for a few days or weeks before they must surface. And surfacing isn't an option when you're trapped beneath a glacier. Then there's the pressure. The deeper beneath the ice you go, the greater the weight above you. At depths of several kilometers, the pressure reaches hundreds of atmospheres, enough to crush most materials if they're not engineered with extreme precision. The ice itself exerts additional mechanical stress. As it flows, it grinds against the rock below, creating friction and shear forces that can tear apart equipment. meltwater channels open and close unpredictably, sometimes flooding with sudden torrents, other times freezing solid. Even the most carefully designed probe can find itself immobilized or destroyed by forces we still don't fully understand. This is part of why exploration beneath the Arctic glaciers has advanced so slowly. Every attempt teaches us more about what we don't know and how little we're prepared for the conditions that await us. It's tempting to think of the Arctic as static, a frozen, unchanging wasteland. But that's one of the biggest misconceptions about it. The glaciers are constantly moving, flowing outward from their centers of accumulation toward the sea. That movement can be measured in meters per year, but over decades or centuries, it reshapes the entire landscape beneath the ice. Caves collapse, lakes migrate, channels are swallowed, and new ones form. Even the thickness of the ice changes as snow accumulates, melts, refreezes, and compacts. For explorers, that means the target you're aiming for may not even exist by the time you reach it. A subglacial lake detected by radar today might have drained through a hidden channel by the time a drill arrives years later. A stable ice shelf might become riddled with crevasses and fractures after a season of warming. The Arctic is not a frozen tomb, it's a living, moving system, and that makes it a constantly shifting puzzle. Climate change is making that puzzle even harder. The Arctic is warming nearly 4 times faster than the global average. Sea ice is thinning and retreating. Glaciers are melting at unprecedented rates, and the delicate balance of pressure and temperature beneath the ice is shifting. On one hand, that makes some areas more accessible. Thinning ice can be easier to penetrate, and new channels might allow waterborne probes to explore further. On the other hand, it makes conditions more unpredictable and dangerous. Ice shelves that once provided stable platforms for research now fracture and collapse. Meltwater can refreeze in unexpected ways, sealing off routes and trapping equipment, and the very ecosystems we hope to study might be disappearing before we ever reach them, altered or destroyed by the rapid changes above. The window to study what lies beneath may be narrowing, even as our ability to reach it slowly improves. Despite these obstacles, scientists remain determined. The Arctic holds clues to some of the biggest questions in science. Questions about life, climate, and even other worlds. Subglacial environments could harbour microbial life forms adapted to conditions we once thought uninhabitable. Studying them could reveal how life persists in extreme environments, offering clues to how it might exist on icy moons like Europa or Enceladus. The sediments beneath the ice hold records of past climates, locked away in undisturbed layers that stretch back hundreds of thousands of years. Unlocking those records could help us understand how Earth's climate has changed and how it might change again. And the physical processes beneath the glaciers could teach us about ice dynamics, sea level rise, and the future of our polar regions in a warming world. But to access those secrets, we must solve the problem that has defied us for decades: how to safely, cleanly, and effectively reach beneath the Arctic's frozen shield. There are ideas on the horizon. Some researchers are developing cryobots, robotic probes designed to melt their way through ice using heat from nuclear power sources. These devices could, in theory, descend through kilometers of ice, carrying instruments to study the high water and sediment below. Others are experimenting with laser drilling, using focused energy beams to cut narrow shafts through ice without the contamination risks of traditional methods. Still others propose hybrid systems that combine drilling with autonomous navigation, deploying swarms of small probes that work together to map and monitor the under-ice world. Each of these ideas faces enormous technical and logistical hurdles, but they represent a growing determination to pierce the veil beneath the North Pole. Whether any of them will succeed remains to be seen. For now, the Arctic beneath the ice remains one of the last great mysteries on Earth. A place we know exists but cannot yet reach. A hidden realm shaped by pressure, darkness, and time. Every attempt to explore it teaches us something new about our planet and about the limits of our technology and understanding. But it also reminds us of something deeper. the Earth still holds secrets from us. In an age where satellites map every mountain and drones scan every rainforest, the idea that an entire landscape, perhaps an entire ecosystem, could remain hidden beneath our feet is both humbling and thrilling. It's a reminder that exploration isn't just about going farther or faster. Sometimes it's about finding a way to go deeper, into places that resist us, challenge us, and refuse to give up their mysteries easily. And as we look closer at this frozen kingdom, we begin to realize that the problem isn't just about building better drills or stronger robots. It's about confronting the fundamental physics of ice itself, the weight, the pressure, the movement, the constant reshaping of the world beneath our feet. And it's about understanding how those forces interact with the machinery we build and the ambitions we bring. Because beneath the surface of this icy realm lies a truth that has shaped it for millions of years, a truth that will shape everything we try to do there. And to see that truth clearly, we have to look not just at the surface, or even the ice itself, but at the forces that hold it all together and make it so difficult to breach. If you were to stand on the ice near the top of the world and press your hand against its surface, you might think you were touching something delicate. Ice fractures under pressure. It melts when warmed. It can be shattered with a hammer or carved with a blade. It feels fragile, temporary, something that should yield easily to human tools and machines. But beneath your feet, that thin sheet extends downward into a body of frozen water so vast, so heavy, and so relentless that it bends the land beneath it and alters the shape of the planet itself. The glaciers of the Arctic are not delicate. They are ancient, monstrous accumulations of snow and pressure, built layer by layer over millions of winters, and their weight is one of the fundamental reasons we cannot yet truly explore the world beneath them. Every snowflake that has ever fallen on the polar ice contributes to this immense weight. It begins with something almost laughably small, tiny crystals drifting silently down from the sky, stacking atop one another through storms and seasons, year after year. Most melt away when summer sun returns, but those that don't become part of something larger. As they pile up, the snow at the bottom is compressed by the layers above, its delicate latticework collapsing under the weight until it transforms into fern, a granular intermediate between snow and ice. Over centuries, as more snow accumulates, that fern becomes dense glacial ice. What was once light enough to be carried by the wind becomes heavy enough to reshape continents. The Greenland ice sheet alone, the largest body of ice in the northern hemisphere, contains about 2.9 million cubic kilometers of frozen water. That's enough to cover the entire United States in ice more than 300 meters thick. Its weight is measured not in tons, but in trillions of tons, and that weight does not sit still. Ice flows. It does not flow quickly, at least not in human terms. But over decades and centuries, it behaves less like a solid and more like an incredibly slow, viscous liquid. Under the relentless pressure of its own mass, glacier ice deforms and moves outward from its thickest points, creeping toward the sea in currents that carry rock and debris with them. This movement isn't uniform. It varies with temperature, bedrock friction, meltwater lubrication, and countless other factors. But no part of a glacier is truly stationary. Even the thickest ice, which might seem frozen in place, is creeping millimeters or centimeters each day. And the deeper you go beneath that ice, the more intense the pressure becomes, squeezing rock, water, and even the glacier itself into new shapes. For humans and machines trying to penetrate this frozen world, that movement is an enemy we have yet to conquer. It bends drilling shafts, closes tunnels, crushes anything that lingers too long. To grasp just how overwhelming this pressure is, consider the numbers. For every 10 meters of ice above a point, there's roughly 1 atmosphere of pressure, about 14.7 pounds per square inch. That means that beneath 1,000 meters of ice, the pressure exceeds 100 atmospheres. At 3,000 meters, as at the base of parts of the Greenland ice sheet, the pressure surpasses 300 atmospheres, more than 4,400 pounds per square inch. Few materials on Earth can withstand such force indefinitely without deforming. Steel can bend, glass can shatter. Even rock will yield and flow over geological time. At those pressures, water behaves differently too. Its melting point drops, allowing it to remain liquid even when temperatures are below freezing. That means at the base of a glacier, where pressure is highest, liquid water often exists in thin layers or pockets, lubricating the ice above and helping it slide over the bedrock. This, meltwater, is vital to the glacier's movement, but it also creates unpredictable conditions for explorers. A drill can suddenly encounter liquid water after kilometers of solid ice, destabilizing the borehole and threatening contamination of pristine subglacial environments. The pressure doesn't just act vertically. As the glacier flows outward, it exerts immense horizontal forces as well, grinding against the valley walls and the bedrock below. The base of a glacier is not smooth. It's a chaotic zone of rock fragments, sediments, and meltwater, all being dragged along under crushing weight. This process, called glacial erosion, has carved out some of the world's most dramatic landscapes: U-shaped valleys, fjords, basins that were once buried beneath miles of ice. But it also means that the interface between ice and bedrock is constantly changing. Cavities open and close, water channels shift, sediment builds up and is swept away. For any machine attempting to operate in this environment, predictability is nearly impossible. A probe lowered into one channel might find it sealed off by refreezing water days later. A drilling shaft might emerge into a cavity that didn't exist when the project began. The glacier is always reshaping itself, always rewriting the landscape below. This constant pressure also changes the shape of the land itself. The Earth's crust, though seemingly rigid, is elastic on long timescales. When a massive glacier forms, its weight pushes the crust downward, depressing the land beneath it. This phenomenon, known as isostatic depression, can lower the surface by hundreds of meters. When the glacier melts, the crust slowly rebounds, a process called isostatic rebound. But it can take thousands of years. In places like Canada and Scandinavia, the land is still rising today as it recovers from the weight of ice sheets that melted at the end of the last ice age, more than 10,000 years ago. Under the Arctic glaciers, this interplay between ice and rock is ongoing. As the ice thickens and thins, advances and retreats, it flexes the crust below, altering groundwater flow, creating new channels and reshaping the very foundations of the landscape. That means the world beneath the ice isn't just hidden, it's alive, dynamic, constantly changing under forces far beyond our control. It's not only the land that feels this pressure. The ocean beneath the Arctic sea ice is also affected. Sea ice might seem thin compared to the Greenland ice sheet, but it still exerts significant weight over vast areas. That weight pushes down on the water below, altering currents and mixing patterns. Combined with the pressure from the glaciers that spill into the sea, it shapes the circulation of the Arctic Ocean itself. This circulation in turn influences the distribution of nutrients, the formation of deep water masses, and even global climate patterns. The Arctic is a crucial engine in Earth's climate system, and the weight of its ice is one of the pistons driving that engine. Any attempt to explore beneath it must contend not only with the pressure of the ice itself, but with the ocean it helps shape, a dynamic, powerful body of water that is as much a part of the system as the ice above it. For the machines we design, this pressure is more than a nuisance. It is a fundamental barrier. Traditional drilling equipment is built for rock, not ice. It's designed to bore through relatively stable materials under predictable conditions. In ice, everything is different. The material flows, it melts and refreezes, it exerts pressure in unpredictable ways. Drill shafts can buckle under the stress. Boreholes can close as the ice flows around them. Meltwater can refreeze above the drill bit, trapping it deep within the glacier. And even if the equipment survives the journey downward, the conditions at the base, crushing pressure, unpredictable water pockets, unstable sediments, can render it useless. Building machines that can operate reliably in these conditions requires not just stronger materials, but entirely new approaches to engineering. Even the most advanced robotic probes face similar challenges. Autonomous underwater vehicles designed to explore beneath ice must withstand immense pressure while navigating through complex, shifting environments. Their hulls must be strong enough to resist crushing forces, yet light enough to allow for mobility. Their sensors must function in conditions of near total darkness and intense cold. Their power systems must operate reliably even as temperatures plunge and pressures climb. And perhaps most challenging of all, they must do all of this without direct communication. Radio waves can't penetrate thick ice, and acoustic signals degrade quickly, leaving the robots largely on their own once they enter the under-ice environment. A failure deep beneath a glacier doesn't just mean the loss of expensive equipment, it means the loss of data, of progress, of years of preparation and planning. The pressure also poses a risk to what we're trying to study. If subglacial lakes and ecosystems exist beneath the Arctic ice, they have evolved in conditions that are almost entirely sealed off from the surface. Introducing even a small amount of contamination could irreversibly alter those environments, but sterilizing equipment for use under such pressure is extraordinarily difficult. Materials that are sterile at the surface may be compromised under hundreds of atmospheres of force. Fluids used in drilling can behave unpredictably, expanding or contracting in ways that create pathways for contamination. Even the act of drilling itself, the heat generated, the vibrations produced, can disturb delicate environments. Balancing the need to explore with the need to protect these pristine systems is one of the greatest ethical and scientific challenges we face. It's easy to underestimate just how much time is embedded in that pressure. Each layer of ice represents a winter. A season of snow that fell and never melted, compressed into the fabric of the glacier. In some places, the ice at the base of Greenland's sheet is more than 1 million years old. That means the water trapped beneath it has been sealed away since before modern humans existed. The pressure we encounter there is not just physical, it's temporal. It's the weight of countless winters pressing down, season after season, century after century, until the past itself becomes a barrier. Every attempt to penetrate that barrier is an attempt to move through time, to reach back into Earth's distant history, and touch a world that has been untouched for longer than we can comprehend. And yet, the weight is not constant. Climate change is reshaping the Arctic, altering the balance of ice and water and changing the pressures beneath the surface. As temperatures rise, glaciers thin and retreat, reducing the weight they exert on the land below. This can trigger isostatic rebound, altering drainage patterns and potentially exposing subglacial environments to new conditions. It can also destabilize ice sheets, accelerating their movement and increasing the frequency of calving events where massive chunks of ice break off into the sea. These changes make exploration even more complex. A site chosen for drilling might become unstable before the project begins. A channel mapped 1 year might be gone the next. The very weight that has preserved these hidden worlds for millions of years is now shifting, sometimes faster than our technology can adapt. This shifting weight also carries global consequences. As glaciers melt and lose mass, they contribute to rising sea levels, reshaping coastlines and threatening communities thousands of kilometers away. The meltwater they release alters ocean salinity and circulation, influencing weather patterns and marine ecosystems. The pressure they relieve on the Earth's crust can even trigger earthquakes and volcanic activity, subtle reminders that the cryosphere and the geosphere are deeply interconnected. Exploring beneath the Arctic ice isn't just about curiosity, it's about understanding processes that affect the entire planet. But those processes are governed by forces far greater than us. Forces measured in millions of winters and trillions of tons, and so the weight of 1 million winters remains one of the most formidable barriers between us and the world beneath the Arctic ice. It crushes our machines, distorts our measurements, reshapes the landscape faster than we can map it. It hides water where we don't expect it and seals it away where we hope to find it. It preserves ancient ecosystems while threatening to destroy them if disturbed. It is not a simple obstacle we can drill through or melt away. It is a force that defines the environment itself, shaping everything that happens beneath the ice, and everything we try to do within it. But understanding that weight, learning how to work with it rather than against it, is key to unlocking the secrets beneath the glaciers. It forces us to rethink how we design our tools, how we plan our missions, and how we imagine exploration itself. It reminds us that the Arctic is not an empty void waiting to be filled with our discoveries. It is an active, dynamic system with its own rules, its own rhythms, and its own immense inertia. And as we push deeper into its frozen heart, we begin to see that the problem is not just the weight pressing down from above. It is also the darkness that lies beneath, a darkness that has never known sunlight, never felt warmth, and holds within it mysteries older than memory itself. Far below the frozen skin of the Arctic, where no sunlight has ever reached and no eye has ever seen, there is a darkness that does not simply exist, it endures. It is older than the first stories humans ever told, older than the earliest tools carved from stone, older even than the landscapes that lie buried beneath it. It has been there since before ice covered this part of the world, before the continents settled into their current shapes, before mammals walked the earth. It is a darkness that has persisted, unbroken, for millions of years, sealed beneath the weight of ice and the indifference of time. And it is into this darkness that we would have to go if we ever hope to truly explore beneath the glaciers of the North Pole. It is not the kind of darkness we encounter when the sun sets or when a light switch is flipped. Those are temporary, superficial darknesses, thin veils that can be pierced by a candle or a flashlight. This is a darkness so absolute, so total, that it seems to erase the very concept of a light. It is the product of kilometers of ice, each meter scattering, absorbing, and blocking every photon that tries to pass through. Even in the clearest ice, sunlight penetrates only a few dozen meters. Beyond that, even the faintest trace of daylight disappears. Deeper still, the pressure increases, the temperature plummets, and the ice becomes opaque, clouded with bubbles, sediments, and layers formed by thousands of winters. By the time you reach the base, perhaps 2 or 3 kilometers below the surface, light is not just absent, it is irrelevant. There is nothing for it to reflect from, nothing for it to reveal. The darkness is not waiting to be illuminated, it simply is. This absence of light creates conditions that are almost alien. Human senses are built around light. Our eyes evolved to detect it. Our biology relies on it to regulate cycles of sleep and wakefulness. Our perception of space and movement depends on it. Without light, those senses falter. Even our machines struggle. Cameras are useless without artificial illumination. Lasers scatter unpredictably in cloudy ice. Sonar, often the best alternative, paints only crude outlines of what lies beyond. Every attempt to explore in this environment feels like groping through an endless void, each piece of data incomplete, each measurement shadowed by uncertainty. It's not just that we cannot see, it's that the very tools we rely on to compensate for sight are limited, distorted, or defeated by the conditions. But the darkness is more than just a lack of light. It is also a product of isolation. The ecosystems beneath the ice, if they exist, have been sealed away from the surface world for hundreds of thousands, or even millions of years. They have never seen the sun. They have never experienced day or night as we know them. Their rhythms, if they have any, are dictated by entirely different forces. The slow flow of meltwater, the chemical reactions between rock and water, the faint geothermal heat rising from below. In this darkness, life would have to exist without photosynthesis, relying instead on chemosynthesis, the extraction of energy from chemical reactions rather than sunlight. Such ecosystems exist elsewhere on Earth, most famously around hydrothermal vents on the ocean floor, where bacteria feed on minerals and support entire communities of organisms in total darkness. If similar life exists beneath the Arctic ice, it would represent not just a remarkable adaptation, but an entirely different way of being, one that has thrived beyond the reach of light for longer than our species has existed. This possibility is one of the most tantalizing reasons scientists want to reach these hidden worlds. The study of extremophils, organisms that live in conditions previously thought uninhabitable, has transformed our understanding of life's resilience. Microbes have been found in boiling hot springs, inside nuclear reactors, deep within Earth's crust, and in Antarctic subglacial lakes buried under kilometers of ice. If life exists beneath the Arctic glaciers, it would add to this growing list of environments where biology defies expectations. More importantly, it would offer clues about how life might exist elsewhere in the universe. Icy moons like Europa and Enceladus are thought to have subsurface oceans beneath thick crusts of ice. If life can persist in the lightless, pressurized, chemically driven environment beneath the North Pole, it might also exist in the dark oceans of those distant worlds. Exploring this darkness is not just about understanding our own planet. It's about probing the boundaries of life itself. Yet even if no life exists there, the darkness still holds secrets worth pursuing. The sediments trapped beneath the ice record a history of Earth's climate stretching back hundreds of thousands, perhaps millions of years. Each layer of sediment is a page in that history, recording changes in temperature, atmospheric composition, ocean circulation, and even volcanic activity. Accessing those sediments could help scientists reconstruct the story of Earth's past climate and improve predictions of its future. But those sediments are sealed beneath ice and darkness, protected by conditions that make them extraordinarily difficult to reach. Drilling through kilometers of ice is challenging enough. Extracting uncontaminated samples from a pitch-black, pressurized, and often waterlogged environment at the base is even harder. And even if we succeed, interpreting what we find is no simple task. The darkness preserves, but it also distorts. Layers can be disturbed by the movement of the ice above. Sediments can be mixed by meltwater flows. Signals can be lost or altered. Each sample is a puzzle, a fragment of a story written in a language we're still learning to read. The darkness also shapes the physical environment in ways that complicate exploration. In the absence of sunlight, temperatures remain consistently low, often far below freezing. The ice above insulates the base, trapping geothermal heat and creating a delicate balance between freezing and melting. Small changes in temperature or pressure can shift that balance dramatically. A slight increase in heat might create a meltwater channel where none existed before. A small decrease might freeze a passage shut. These changes can occur unpredictably and can render carefully planned exploration efforts useless. A borehole that reaches liquid water one year might encounter solid ice the next. A meltwater channel mapped by radar might have vanished by the time a probe arrives. The darkness hides these changes from us, leaving us to infer them from indirect evidence and guesswork. And then there's the psychological dimension of darkness, something we don't often consider, but which matters deeply in environments like this. Humans are not built for absolute darkness. Even in the deep ocean, bioluminescent organisms provide faint glimmers of light. Beneath the Arctic glaciers, there may be no such light at all. For explorers and scientists working in these conditions, the absence of visual cues can be disorienting, even disturbing. Time loses its meaning when there's no sunrise or sunset. Space becomes abstract when there's nothing to see. Machines too face challenges in this sensory vacuum. Navigation systems that rely on visual landmarks become useless. Cameras designed to detect light must rely on artificial illumination, which can alter the environment and affect the very things we're trying to study. Even sonar, which uses sound instead of a light, struggles to provide high-resolution images in the complex, shifting geometry beneath the ice. This sensory deprivation is one reason why exploring beneath the Arctic ice is often compared to exploring space. Both environments are extreme, hostile, and utterly alien to human senses. Both require technology that can function without direct human control. Both demand careful planning and meticulous attention to contamination and safety. And both offer the possibility of discoveries that could transform our understanding of the universe. But there is one crucial difference. Space is empty, the darkness beneath the Arctic is not. It is filled with water, ice, sediment, pressure, and potentially life. It is a darkness that is alive in ways we can barely imagine, shifting, flowing, reacting, evolving, even in the absence of a light. Some might ask why darkness matters. After all, we have technology that can create light. We have lamps, lasers, and sensors that can illuminate even the deepest ocean trenches. But the problem is not simply lighting the way. It's that light behaves differently in this environment. In water, light scatters and absorbs quickly, losing intensity and coherence. In ice, the scattering is even more pronounced, and impurities like air bubbles and sediments can bend or block light entirely. Artificial illumination might reveal what is immediately in front of a probe, but it cannot pierce the darkness beyond a few meters, and even when it does, it can change what we see. Light introduces heat, which can alter the delicate thermal balance of the environment. It can also affect chemical reactions or biological processes, potentially disturbing the very systems we want to observe in their natural state. The darkness, then, is not just an obstacle, it is a defining feature of the environment beneath the Arctic ice. It shapes everything that exists there, from the physical structure of the ice to the chemical composition of the water, from the behavior of any potential life forms to the preservation of ancient sediments. And because it is so absolute, it also shapes our ability to explore. We are creatures of light trying to navigate a world that has never known it. Every tool we build, every mission we plan, must account for that fundamental difference. We must learn to sense without seeing, to map without light, to study without disturbing. That requires technologies and techniques we're only beginning to develop, and a mindset that embraces the unknown rather than trying to banish it with illumination. There's also something profoundly humbling about this darkness. It reminds us that not everything on Earth is accessible to us, that there are still places where our knowledge ends and mystery begins. In a world where satellites can map every mountain and drones can photograph every forest, it is easy to believe that nothing remains hidden. But beneath the Arctic ice, hidden in darkness older than memory, there is a realm that has never felt the touch of sunlight, never echoed with human footsteps, never been mapped or measured. It is a reminder that the Earth still holds secrets, and that some of those secrets lie not in distant galaxies or exotic planets, but right here beneath our feet. For scientists, that humbling realization is also a source of motivation. Every time we push a little deeper into that darkness, we learn something new about ice dynamics, about climate history, about the limits of life. Every failure teaches us how to build better tools. Every unexpected discovery reshapes our understanding of what's possible, and every unanswered question fuels the desire to go further. The darkness is not just a barrier, it is an invitation, a challenge from the Earth itself, to see how far our curiosity and ingenuity can take us. But even as we learn to work within that darkness, we must also remember that it is not static. Like the ice above it, it changes. It shifts as the glaciers advance and retreat. It deepens as layers of ice build up. It thins as melting accelerates. It moves as channels open and close. The darkness that exists beneath the Arctic today is not the same as the darkness that existed 1,000 years ago, and it will not be the same 1,000 years from now. That means that every attempt to explore it is a race against time, a chance to capture a glimpse of a world that may soon be gone or transformed beyond recognition. And that leads us deeper still into the question of what lies within this darkness, beyond the reach of light and the grasp of our current technology. Because hidden in that void are not just sediments and water and rock. There may also be entire networks of subglacial rivers and lakes flowing unseen beneath the ice. There may be chemical processes at work that we have never observed. There may be forms of life that evolved in ways we have yet to imagine. The darkness hides them all, not out of malice, but simply because it is what it is. Ancient, immense, indifferent. Beneath the glaciers of the far north, in a place where light has never reached, and sound moves slowly through dense, frozen silence, There may be entire worlds of water sealed away from everything we know. They are not oceans in the way we imagine them when we think of the Pacific or the Atlantic. They do not roar with waves or sparkle beneath sunlight. They are oceans without shores, without tides, without a surface. They flow through tunnels and basins beneath kilometers of ice, trapped and forgotten, shaped by pressure and time. They exist, if they exist, in total darkness, hidden from the rest of Earth for hundreds of thousands or even millions of years. And they may hold secrets about the history of our planet, about the nature of life, and about the limits of exploration itself. Scientists call them subglacial lakes, but that term hardly does justice to what they might be. The word lake suggests something placid and contained. But beneath the ice, water is neither. Under immense pressure, even small amounts of heat from friction, from geothermal energy, from the weight of the ice itself, can melt the base of a glacier. That meltwater doesn't stay still. It flows into depressions, carves channels through the sediment, gathers in pockets and basins, and forms networks that can stretch for hundreds of kilometers. Some of these pockets remain sealed for tens of thousands of years. Others connect to one another, creating entire hidden drainage systems beneath the ice. Some drain suddenly in massive floods that reshape the landscape below. Others may persist quietly, isolated and undisturbed, sealed beneath ice so thick that not a single molecule of their water has touched the atmosphere since long before humans evolved. We know these hidden oceans exist beneath Antarctica. Lake Vostok, the largest of them all, lies beneath nearly 4 kilometers of ice and spans more than 12,000 square kilometers, roughly the size of Lake Ontario. It has been sealed off from the surface for at least 15 million years. Over 400 other subglacial lakes have been identified beneath Antarctica, each with its own shape, depth, and hydrological behavior. In Greenland, scientists have identified more than 50 subglacial lakes beneath the ice sheet, though most are smaller than their Antarctic counterparts. And beneath the sea ice of the Arctic Ocean, though direct evidence is scarce, models suggest that similar pockets of meltwater could exist where pressure, geothermal heat, and topography allow it. These are the hidden oceans we dream of, not vast open expanses, but labyrinthine networks of water beneath ice, flowing unseen and untouched. What makes these hidden oceans so fascinating is not just their existence, but their potential. They're among the most isolated environments on Earth, sealed away from sunlight, shielded from atmospheric exchange, and protected from surface contamination. They may have remained stable for vast stretches of time. Within them, chemical reactions driven by minerals in the bedrock or by the slow decay of radioactive elements could provide energy. Microorganisms, if they exist, might thrive on that energy, forming entire ecosystems independent of the surface world. They would not rely on photosynthesis, which requires light, but on chemosynthesis, using chemical reactions to sustain life. This is how life thrives around hydrothermal vents on the ocean floor, where sunlight never penetrates, and volcanic activity provides heat and energy. If life can do the same beneath glaciers, it would be living proof that biology can persist in darkness, isolation, and extreme pressure. The implications of that are profound. If life can exist beneath the Arctic glaciers, it strengthens the possibility that life could exist elsewhere under similar conditions. On Europa, one of Jupiter's moons, a global ocean is thought to lie beneath a crust of ice tens of kilometers thick. On Enceladus, a moon of Saturn, geysers of water erupt from cracks in its icy shell, hinting at a subsurface ocean below. Both moons receive little sunlight, and both are too cold for liquid water on the surface. Yet beneath their icy crusts, heat from tidal forces and radioactive decay may sustain liquid water and possibly life. Studying subglacial lakes on Earth could offer a preview of what those extraterrestrial oceans might be like. They are analogues, models, test cases, ways to study how life might arise, evolve, and survive in environments far removed from sunlight and surface conditions. But these hidden oceans are not just interesting because of what might live within them. They're also archives of Earth's past. The sediments at their bottoms may contain records of climate change, volcanic eruptions, and even asteroid impacts stretching back millions of years. Trapped gases could preserve snapshots of ancient atmospheres. Layers of deposited material could reveal shifts in ocean circulation, ice sheet dynamics, and global temperature. Unlocking these records could transform our understanding of how Earth's climate has changed over geological time and how it might change in the future, but accessing them is extraordinarily difficult. The very isolation that makes these lakes valuable also makes them fragile. A single drilling operation could contaminate them, altering their chemistry, or introducing microbes from the surface. A single miscalculation could collapse a channel or drain a lake entirely. Every attempt to reach these hidden oceans carries risks, and those risks increase with depth, pressure, and complexity. Part of what makes exploration so challenging is that these lakes are not static. They fill and drain over time, responding to changes in pressure, temperature, and ice movement. Some may remain stable for tens of thousands of years, while others drain and refill on timescales of decades or even years. These drainage events can have dramatic consequences. When a subglacial lake drains, it can release billions of litres of water in a matter of days, carving channels beneath the ice and accelerating the glacier's flow. These sudden floods, known as jökullaups, can reshape landscapes and even impact sea level. For scientists, they also mean that a target chosen for exploration might not exist in the same form by the time they arrive. A lake identified by radar one year might have drained the next. A channel mapped in one season might have shifted course by the following. The hidden oceans beneath the ice are not frozen in time. They are dynamic, evolving systems, and that makes them both more interesting and more difficult to study. Another obstacle is the sheer inaccessibility of these environments. Drilling through kilometers of ice requires immense amounts of energy, precision, and patience. Traditional drilling methods, which rely on physical cutting or the circulation of drilling fluids, risk contaminating the environment or becoming trapped as the ice flows and refreezes. Thermal drills, which melt their way downward, face challenges of their own. They require enormous power and must prevent the water above them from refreezing and sealing the borehole. Even if a drill reaches a subglacial lake, retrieving samples without contamination is a delicate process. The water is under high pressure and may gush upward into the borehole, carrying sediments and microbes that could compromise the sample. Specialized systems must be used to capture water and sediment cleanly, maintain pressure conditions, and preserve the environment below. Because of these challenges, much of what we know about subglacial lakes comes from indirect evidence. Radar and seismic surveys reveal their outlines. Satellite measurements detect subtle changes in ice elevation that indicate filling and draining. In some cases, water from subglacial lakes emerges at the glacier's edge, carrying sediments and microorganisms that hint at what lies beneath. But these glimpses are incomplete. They tell us that the hidden oceans exist, but not how they function, what they contain, or how they change over time. They leave us with tantalizing hints but few definitive answers, and so the hidden oceans remain largely in the realm of imagination, places we dream about but cannot yet touch. That imagination has grown richer in recent years as scientists develop new technologies designed to reach these remote environments. One promising approach is the cryobot, a robotic probe that melts its way through ice using heat, often generated by a nuclear power source. Unlike traditional drills, cryobots do not require boreholes to remain open, and they can operate autonomously, carrying sensors and sampling equipment directly into the lake. Once there, they can deploy smaller robots or collect samples before returning data to the surface. Another approach involves hot water drilling, in which high-pressure jets of heated water melt a path through the ice. This method has been used successfully in Antarctica to access shallow subglacial lakes, and researchers hope it can be adapted for deeper Arctic environments. Advances in autonomous underwater vehicles also hold promise. These machines could enter subglacial lakes through narrow openings and explore them directly, mapping their interiors and searching for signs of life. Despite these advances, the challenges remain immense. Communication through thick ice is limited, making it difficult to control or retrieve data from robotic probes. Power is a constant constraint, both for drilling and for sustained exploration beneath the ice, and contamination remains a serious concern. Any mission must adhere to strict cleanliness protocols to avoid altering the pristine environments below. These constraints mean that exploration progresses slowly, often over decades. Each mission requires years of planning, testing, and refinement. Each attempt builds on the lessons of those before it. And each discovery, however small, brings us closer to the hidden oceans we seek. The dream of exploring these hidden oceans is not just scientific, it's also deeply human. There is something about the idea of vast, unseen worlds beneath our feet that captures the imagination. It reminds us that even on a planet we've mapped in exquisite detail, there are still places we do not know. Places that have existed in isolation for longer than we have walked the Earth. It reminds us that exploration is not just about reaching distant planets or probing distant stars. It's also about looking inward into the hidden corners of our own world. The oceans beneath the Arctic ice are not remote in the way Mars or Europa are. They're here, beneath our own planet's surface, waiting for us to find a way to reach them. And yet, perhaps part of their allure lies in their inaccessibility. There is something profoundly compelling about a mystery that resists us, that refuses to yield no matter how hard we try. It humbles us, reminding us that we are not masters of this planet, but participants in its ongoing story. It challenges us, pushing us to invent new tools, new methods, new ways of thinking, and it inspires us, fueling the imagination with visions of what might be waiting in the darkness. Strange ecosystems, ancient sediments, chemical processes that have never seen the light of day. These are the hidden oceans we dream of. And though they remain beyond our reach for now, the dream itself drives us forward. As we chase that dream, we begin to understand that exploring beneath the Arctic ice is not just about water or life or history. It's also about the tools we build and the limits we confront. Every attempt to reach these hidden oceans has taught us something about what our machines can and cannot do. Every setback has revealed a new challenge: pressure that crushes steel, ice that flows and refreezes, channels that shift and disappear. The Arctic seems determined to remind us that it plays by its own rules, and that to explore beneath its glaciers we must learn those rules and build accordingly. And so our understanding now turns toward the machines we've built and the ways they've succeeded, failed, and adapted in the face of one of the most challenging environments on Earth. Because for all our ambition, all our restless curiosity, and all the centuries we've spent turning questions into discoveries, we are still fragile creatures trying to reach into places that were never meant for us. And nowhere is that fragility more obvious than in our attempts to send machines into the frozen underworld beneath the Arctic glaciers. Every bolt of steel, every circuit board, every meticulously engineered drill and probe is a testament to human ingenuity. And yet, in the presence of ice that weighs trillions of tons, water that moves unseen in darkness, and pressure that can crush a submarine like a soda can, our machines look clumsy, small, and profoundly mortal. They stand at the edge of a world we cannot enter ourselves, built to touch what we cannot touch, to see what we cannot see. And still, for now, that world mostly remains beyond their reach. We have been building machines to explore hostile environments for as long as we've had machines at all. Deep-sea submersibles that withstand crushing pressure, rovers that crawl across alien landscapes, spacecraft that endure the cold emptiness beyond our planet. But the environment beneath the Arctic glaciers is unlike any other, and the tools we've built for one extreme do not easily adapt to another. It's a place where ice behaves both like a solid and a liquid, where water flows under pressures hundreds of times greater than those at the surface, where communication is nearly impossible, and where everything, temperature, structure, chemical composition, changes constantly and unpredictably. A machine designed for the deep ocean cannot simply be lowered beneath the ice. A drill built to pierce rock cannot be expected to survive kilometers of shifting, deforming glacier. To explore this hidden world, we've had to design tools that are as specialized and resilient as the environment is hostile. One of the first tools humans ever used to peer beneath Arctic ice was the nuclear submarine. During the Cold War, American and Soviet submarines prowled beneath the polar ice cap, navigating blind through a maze of shifting floes and jagged keels. These missions were feats of engineering and navigation, proving that humans could travel beneath ice for extended periods. But even these immense, powerful vessels were limited. They travelled beneath sea ice, not beneath glaciers. They stayed in open water, far from the chaotic interfaces where ice meets land or rock. And though they could map the underside of the ice and gather data about the water column, they could not approach the places where the real mysteries lie. The deep pressurized zones beneath grounded ice sheets where subglacial lakes and rivers hide. Submarines, for all their power, are too large, too blunt, too ill-suited for the precision and delicacy that such environments demand. To go deeper, scientists turned to drilling. The logic was simple enough. If we cannot go beneath the ice from below, perhaps we can go through it from above. Drilling into glaciers is not new. Ice cores have been extracted for decades to study past climates, but drilling all the way through to the base is another matter entirely. It is slow, difficult, expensive work. The ice is not uniform. It changes composition, density, and temperature. As you descend, layers of compressed snow give way to ancient ice riddled with bubbles and sediments. Pressure increases steadily, and the ice begins to behave plastically, flowing around the borehole and threatening to close it. Traditional rotary drills, which work well in rock, struggle here. They rely on drilling fluids to carry cuttings to the surface and prevent the borehole from collapsing. But those fluids risk contaminating the pristine environments below. They also require constant maintenance and careful temperature control to prevent refreezing. Even when they succeed, it can take years to drill a single borehole, and one mistake can mean starting over. Thermal drilling offers an alternative. Instead of cutting through ice, these systems melt their way downward using heated water or mechanical heaters to carve a path. Hot water drills have been used successfully in Antarctica, where they can melt through several kilometers of ice in weeks rather than years. They create clean, wide boreholes that can accommodate instruments and sampling devices. But even these systems have limitations. They require vast amounts of energy, often supplied by fuel, that must be transported thousands of kilometers into remote polar regions. They must carefully manage refreezing water, which can seal the borehole or trap equipment, and they are limited by the unpredictable nature of the ice itself. Changes in pressure or temperature can alter the melt rate. A hidden layer of sediment or a sudden influx of meltwater can redirect the drill. It is a delicate balance, and one that is often tipped by forces we cannot fully predict or control. To address the challenge of contamination, scientists have developed sterile drilling techniques that minimize the risk of introducing foreign microbes into subglacial environments. These systems use specially treated drilling fluids, closed-loop circulation, and meticulous decontamination protocols for every piece of equipment. Even so, the risk remains. A single contaminant introduced into a sealed subglacial lake could irreversibly alter its chemistry or disrupt any ecosystem within. For this reason, many projects stop short of breaching the base of the ice. Content to study layers above it, but this caution comes at a cost. It limits our ability to directly sample the water and sediments that hold the most valuable clues. We stand just meters above the unknown, able to sense its presence but not to touch it. While drilling pushes downward from above, another class of machines approaches from below, autonomous underwater vehicles, or AUVs. These robotic explorers are designed to operate beneath ice without direct human control, navigating through complex environments and collecting data as they go. Some are torpedo-shaped, built to glide long distances through water. Others are compact and maneuverable, capable of slipping into narrow crevices and tunnels. Equipped with sonar, cameras, chemical sensors, and even robotic arms, they can map the underside of the ice, measure temperature and salinity, and search for signs of life. AUVs have been used beneath Antarctic ice shelves and sea ice, where they have revealed complex networks of channels and cavities carved by meltwater. They have even ventured into subglacial cavities near glacier grounding lines. places where ice, water, and rock meet in chaotic, shifting equilibrium. But even the most advanced AUVs face formidable obstacles beneath the Arctic ice. Navigation is one of the biggest challenges. GPS signals cannot penetrate water, let alone ice, and acoustic navigation systems are limited in range and resolution. That means AUVs must rely on dead reckoning, calculating their position based on velocity and heading, which accumulates errors over time. Without regular updates, they can drift kilometers off course. Communication is another hurdle. Radio signals cannot pass through thick ice, and acoustic signals degrade quickly, limiting bandwidth and range. Most AUVs must operate autonomously, following pre-programmed instructions and returning to a rendezvous point for data retrieval. If they become stuck, damaged, or lost, there is often no way to recover them. And beneath a glacier, where channels twist unpredictably, ceilings shift, and debris moves with the ice, the risk of losing a vehicle is high. Pressure poses yet another challenge. At depths of several kilometers, the weight of the overlying ice and water can exceed hundreds of atmospheres. AUVs must be built to withstand this pressure without deforming or leaking. Their sensors and electronics must be sealed and insulated against intense cold and crushing force. Batteries too must be capable of operating reliably in near-freezing water under immense pressure, a combination that can shorten their lifespan and reduce their capacity. Every gram of weight and every cubic centimetre of volume must be carefully considered to balance strength, buoyancy, and endurance. And because missions beneath ice can last days or weeks without the possibility of resurfacing, AUVs must carry all the power they need from the start. There are no charging stations beneath a glacier. One of the most ambitious technologies proposed for exploring beneath polar ice is the cryobot, a self-contained robotic probe designed to melt its way downward through ice, carrying instruments with it. Unlike conventional drills, cryobots do not require a borehole to remain open. They move slowly, melting the ice ahead and letting it refreeze behind them. In theory, a cryobot could descend through kilometers of ice, reach a subglacial lake, and deploy instruments, or even smaller robots, into the water. It could collect samples, take measurements, and send data back through a fiber optic cable trailing behind it. Prototypes have been tested in glaciers on Earth, and NASA is exploring cryobot designs as potential tools for exploring icy moons like Europa. But cryobots face many of the same challenges as other machines: power, navigation, communication, contamination. They require enormous amounts of energy to melt their way downward, and once they reach their target, retrieving them may be impossible. If they become stuck or encounter unexpected conditions, they cannot backtrack. They are one-way missions, brave but expendable. Hot water drills, AUVs, cryobots, each represents a different strategy, a different way of approaching the problem, but all of them share a common limitation. They must operate in an environment that does not want them there. The Arctic ice is not passive. It moves, shifts, flows, refreezes. It responds to pressure and temperature in ways that can seal boreholes, crush vehicles, or alter the terrain mid-mission. The water beneath the ice is not static either. It flows through channels that can close or change course. It carries sediments that can clog sensors or damage equipment. It can surge suddenly if a subglacial lake drains, or remain still for centuries. Every machine that enters this environment must contend with forces that are indifferent to its presence. Forces that can undo years of planning in moments. And yet, for all these difficulties, progress is being made. Each failed mission teaches engineers something new about how to build machines for these conditions. Each lost probe reveals a flaw that can be corrected. Each unexpected result points to phenomena we had not anticipated. The challenges are enormous, but they are not insurmountable. Advances in material science are producing stronger, lighter hulls that can withstand pressure and resist ice abrasion. Improvements in battery technology are extending mission durations. New navigation algorithms are reducing drift and improving autonomy, and innovations in communication, from acoustic modems to fiber optic tethers, are expanding the range and reliability of data transmission beneath ice. These incremental advances may not sound dramatic, but they are essential steps toward the day when we can truly explore the hidden world beneath the Arctic glaciers. There's also a growing recognition that no single machine will solve the problem. The environment is too complex, too varied for one tool to do everything. Instead, the future of under-ice exploration likely lies in systems. Networks of complementary technologies working together. A hot water drill might create an access point. A cryobot might descend through the ice. An AUV might then enter the water and explore the lake or channel beyond. Each tool would play a role, each compensating for the limitations of the others. Such integrated missions will be expensive, logistically challenging, and technologically demanding, but they may be the only way to overcome the barriers that have kept the Arctic's hidden world beyond our reach. The machines we build are more than just tools. They're extensions of ourselves, our eyes, our hands, our curiosity made physical. When we send them into places we cannot go, we are, in a sense, reaching there, ourselves. Every sensor reading is a glimpse into the unknown. Every image is a window into a world we have never seen. And every failure is a lesson, a step closer to success. It is easy to think of machines as separate from us, as cold, impersonal devices. But in truth, they are expressions of our deepest desire to know, and the under-ice world of the Arctic is one of the ultimate tests of that desire. Still, even as our machines grow more capable, the environment beneath the ice remains a formidable adversary. It is not simply the darkness, the cold, or the pressure that challenge us. It is the fact that the ice itself is alive in a way that stone or steel is not. It flows, flexes, reshapes itself. It turns passages into dead ends, opens new ones without warning, and crushes obstacles with the patience of time. It is a labyrinth that never stays the same for long, a maze carved by forces older and stronger than us. Beneath the Arctic's frozen crown, the ice is not a monolith. It is not a static, unchanging slab that we can drill through like stone and expect to find the same thing on the other side. It is alive in its own slow, inexorable way. A shifting labyrinth sculpted by physics and time, twisting and reconfiguring itself over centuries and even moments. It creeps forward under its own weight. It fractures and heals. It opens hidden passageways only to close them again. It stretches, flows, and reshapes everything beneath it, constantly redrawing the map we try to follow. And that motion, more than any lack of courage or technology, is why we still cannot truly explore the world beneath the glaciers of the North Pole. When we think of ice, we imagine stillness. We imagine frozen lakes and rigid blocks, crystalline and motionless, but a glacier is not like that. A glacier is a river of ice, slow, viscous, relentless. It moves under the pull of gravity, spreading outward from its thickest points, flowing downhill toward the sea. This flow is not visible to the naked eye in the moment. Stand on the surface, and it will seem as unmoving as a rock. But watch over weeks, months, or decades, and the change is undeniable. Crevasses widen, seracs tilt and collapse. Ice streams, vast, fast-flowing corridors within the ice sheet, surge forward at speeds that can reach several meters per day. Even the most stable parts of the glacier creep forward by centimeters each year, enough to move mountains of ice across continents over the course of millennia. The causes of this movement are deceptively simple. Gravity pulls downward. Pressure builds as more snow accumulates on top. The ice deforms under its own immense weight, flowing outward like honey poured from a jar, though on timescales far beyond human perception. The pressure at the base of the glacier lowers the melting point of ice, allowing thin layers of meltwater to form. This water lubricates the interface between ice and rock, reducing friction and accelerating flow. In places, geothermal heat seeps up from Earth's interior, melting more ice from below and feeding the water system, and the glacier itself grinds against the bedrock, generating frictional heat that further contributes to melting. All of these processes work together in a feedback loop. More meltwater leads to faster flow. Faster flow generates more friction. More friction produces more meltwater. The glacier is not just moving, it is teaching itself how to move faster. But this movement is not uniform. It is complex, variable, and often unpredictable. Some parts of a glacier flow steadily for centuries. Others stop and start, surging forward in sudden bursts before slowing again. These surges can be dramatic. In Alaska, the variegated glacier has been known to surge forward by more than 4 kilometers in just a few months, a pace more than 100 times faster than its usual flow. Such surges happen when water pressure builds at the glacier's base, temporarily lifting it off the bedrock and allowing it to slide forward. When the pressure drops, the glacier settles back into place and the surge stops. Similar surges have been observed in Greenland and other parts of the Arctic, and they can radically alter the glacier's internal structure and the landscape beneath it in a matter of weeks. A channel that existed before a surge may be crushed, a cavity may collapse, a subglacial lake may be drained or split in two. Everything we thought we knew about the terrain beneath the ice can change overnight. Even where flow is steady, it is not uniform across the glacier. Ice near the surface, under less pressure, tends to move faster than ice deep below. Ice near the center of a glacier often flows more quickly than ice along the edges, where friction with valley walls slows it down. These variations create internal stresses that fracture the ice, forming crevasses that can extend hundreds of meters deep. They also create shear zones, where different layers of ice slide past one another at different speeds. These zones are sites of intense deformation, where ice crystals stretch, rotate, and realign in response to the forces around them. The result is a complex, ever-changing internal structure, a labyrinth of layers, bands, and folds that reflect the glacier's history of movement. Any probe or drill descending through this structure must contend with zones of differing density, strength, and flow, each posing its own challenges. The base of the glacier is even more dynamic. Here, where ice meets rock, pressure is greatest, melting is most likely, and movement is most chaotic. Meltwater carves channels through the sediment, linking subglacial lakes into networks that drain and refill unpredictably. As the glacier slides over bedrock, it plucks chunks of rock from the ground, carries them forward, and grinds them into silt. This erosion deepens valleys and widens basins, altering the shape of the bed over time. It also creates obstacles for water flow, forcing channels to reroute and lakes to migrate. Sometimes the glacier seals these channels entirely, trapping water in isolated pockets that can persist for centuries. Other times, a sudden drainage event sends billions of litres of water rushing toward the sea, carving new pathways in days. This constant reshaping means that the subglacial hydrological system is not a static network, but a living, evolving labyrinth, one that we cannot fully map or predict. It's not just the ice and water that move, the ground beneath them does too. The immense weight of a glacier pushes down on Earth's crust, depressing it by hundreds of meters in some places. When the glacier thins or retreats, the crust slowly rebounds, a process called isostatic rebound, altering the slope of the land and the direction of water flow. Over time, this can shift the entire drainage system beneath the ice. Channels that once flowed north may begin flowing south. Lakes that once drained into one basin may spill into another. The glacier responds to these changes, adjusting its flow and reshaping its internal structure in turn. It is a feedback loop that unfolds over millennia, and we're only beginning to understand its complexity. For scientists and engineers trying to explore beneath the Arctic glaciers, this movement is a formidable obstacle. It means that no map stays accurate for long. A cavity identified by radar one year might be gone the next. A borehole drilled into a water channel might miss its target entirely if the channel shifts during the drilling process. Even instruments deployed successfully can be lost or damaged as the ice moves around them. Fiber optic cables can snap. Sensors can be crushed. Probes can be carried away from their intended locations. The glacier does not care about our plans. It moves according to its own rhythms, indifferent to the delicate strategies we design at the surface. Even more challenging is the fact that this movement occurs on many different timescales at once. Some changes happen slowly, over centuries, as ice flows and landscapes evolve. Others happen suddenly, surges, drainage events, collapses, in hours or days. This combination of gradual and rapid change makes prediction extraordinarily difficult. Models that work well over decades fail to capture events that unfold in days. Instruments designed for long-term monitoring can miss the brief but significant episodes that reshape the environment. And because direct observation is so limited, we often don't know these changes have occurred until after they've happened. The labyrinth shifts silently in the dark, and we're left piecing together its movements from fragmentary evidence. Even the sea ice above the Arctic Ocean, though thinner and more transient than glacial ice, contributes to this complexity. Driven by winds and currents, it drifts across the ocean surface, piling up into ridges and splitting apart into leads. This motion exerts stress on the glaciers where they meet the sea, influencing how and where they calve, the process by which chunks of ice break off and form icebergs. Calving in turn can trigger surges in glacier flow or alter the drainage of subglacial water. It can open new pathways beneath the ice or close old ones. It can change the shape of the ice front, affecting how water circulates beneath it. All of these changes ripple through the system, altering the labyrinth below in ways that are difficult to predict. Climate change is amplifying this motion in ways we're only beginning to grasp. Rising temperatures are thinning sea ice and accelerating glacier melt, increasing the amount of meltwater reaching the base of the ice. This can lubricate the glacier bed interface, speeding up flow and increasing the frequency of surges. It can also change the pressure dynamics beneath the ice, triggering drainage events and altering the configuration of subglacial water systems. Warmer air and ocean temperatures can undercut glaciers from below, causing them to retreat more rapidly and destabilizing the labyrinth beneath them. These changes are not uniform. They vary from region to region, glacier to glacier, and even year to year. But they all contribute to a system that is becoming more dynamic, more unpredictable, and more difficult to study. Technology struggles to keep pace with this motion. A radar survey captures a snapshot of the glacier's structure, but that snapshot may be outdated within months. A probe designed to navigate a particular set of channels may find those channels gone or altered by the time it arrives. Drilling through moving ice is like trying to hit a target that is shifting in 3 dimensions while the ground beneath your feet moves too. Even autonomous underwater vehicles, which can adapt to some changes, are limited by the data they have and the paths they can follow. And once a mission is underway, there is often no way to adjust in real time. Communication through kilometers of ice is too slow and unreliable. Decisions must be made based on models that are, at best, educated guesses. All of this creates a paradox for exploration. To understand the labyrinth beneath the ice, we need data, but to get that data, we need to place instruments within the labyrinth. And to do that effectively, we need to know how it moves, which we cannot fully know without data. It is a circular problem, and one that can only be solved through incremental progress. Repeated measurements, improved models, missions that build on the knowledge of those before them. Over time, these efforts begin to reveal patterns in the chaos. Regions of relative stability, cycles of drainage and refreezing, relationships between surface melt and subglacial flow. These patterns do not eliminate uncertainty, but they reduce it, giving us footholds in a shifting landscape. Yet even as our understanding grows, the labyrinth reminds us of its power. It is not a puzzle we can solve once and for all. It is a living system that will continue to evolve long after we're gone. Its pathways will open and close, its lakes will drain and refill, its channels will twist and reroute, and each time we return, it will be different. This reality is both frustrating and exhilarating. It means that exploration will always be challenging, always uncertain. But it also means that there will always be something new to discover, some new mystery hidden in the ever-shifting ice. The labyrinth moves because the glacier is alive, not alive in the biological sense, but alive as a system, responding to forces and feedbacks that shape our planet. High above the Arctic's frozen labyrinth, far from the hidden rivers and sealed-off lakes beneath the glaciers, another force is at work. One that is slower than the tides and subtler than the wind, yet far more powerful than either. It is a force that shapes the thickness of the ice, the speed of its flow, the temperature of its base, and the patterns of water beneath it. It is a force that reaches deep into the frozen heart of the Arctic, without ever touching it directly. That force is climate, and its hidden hand is everywhere. It dictates how much snow falls each winter and how much melts in the summer. It sets the temperature of the air above and the ocean below. It determines how ice forms, how it flows, how it breaks apart, and how it disappears. And as that climate changes, as it warms and destabilizes, it reshapes the labyrinth beneath the glaciers in ways that make exploration harder and more urgent than ever before. For most of human history, the Arctic's climate has been remarkably stable, by our standards. It has swung between ice ages and interglacial periods over tens of thousands of years, yes, but those changes unfolded slowly, giving the ice time to grow and retreat in long measured cycles. Glaciers advanced, carving valleys and pushing sediments before them. Then they melted, leaving behind moraines and reshaped landscapes. As they withdrew, subglacial lakes formed and drained and formed again. The labyrinth shifted, but it did so predictably, in rhythm with the planet's orbital variations and slow changes in greenhouse gas concentrations. But in the last century, that rhythm has been broken. The Arctic is now warming more than twice as fast as the global average, and that rapid change is rewriting the rules that have governed this region for millennia. The most obvious effect of this warming is the thinning of the ice itself. Warmer air temperatures melt ice from above, while warmer ocean waters erode it from below. The Greenland ice sheet, which contains enough ice to raise global sea levels by more than 7 meters, is losing mass at an accelerating rate. Satellite observations show that it is now shedding over 250 billion tons of ice per year, a figure that has more than doubled in just a few decades. Sea ice too is vanishing. Summer sea ice extent has declined by more than 40% since the late 1970s, and the remaining ice is thinner and younger, more prone to melting and breaking apart. These changes are not just surface phenomena, they reverberate downward, altering the pressure at the base of the ice, the temperature of the water beneath it, and the structure of the labyrinth below. As the ice thins, the pressure at its base decreases. This might seem like a small change, but in a system governed by delicate balances, even small shifts can have outsized effects. Lower pressure raises the melting point of water, potentially reducing the amount of meltwater at the glacier bed. That, in turn, can increase friction between ice and rock, slowing the glacier's flow in some places. But the opposite can also happen. Thinner ice is more easily influenced by variations in temperature and meltwater input, making it more sensitive to seasonal changes. Surface meltwater, once confined to shallow layers, can now penetrate deeper into the glacier through crevasses and moulins, vertical shafts that carry water from the surface to the base. When that water reaches the bed, it can lubricate the ice, reducing friction and speeding its movement. In some areas, this has led to a paradox. Even as glaciers thin, they accelerate, surging forward toward the sea and delivering more ice to the ocean. The influx of meltwater also changes the hydrology beneath the ice. In the past, much of the water at the glacier base came from geothermal heat and pressure-induced melting. Slow, steady processes that produced relatively stable water systems. Now, sudden pulses of surface meltwater can flood the subglacial environment, raising water pressure, opening new channels, and altering flow paths. These changes can destabilize subglacial lakes, triggering drainage events that reshape the labyrinth below. They can also cause fluctuations in glacial velocity as variations in basal water pressure influence how easily the ice can slide. For scientists trying to explore beneath the ice, this means that conditions can change dramatically from one season to the next, or even from one week to another. A channel mapped in the spring might no longer exist by autumn. A cavity targeted for exploration might have drained or moved. The labyrinth becomes not just a puzzle, but a moving target. Warming air is only part of the story. The oceans that lap against the edges of the Arctic ice are warming too, and their influence is profound. As warmer waters flow beneath floating ice shelves and glacier tongues, they melt the ice from below, thinning it and destabilizing it. This undercutting can lead to calving events where massive chunks of ice break off and drift away as icebergs. These events in turn can destabilize the glaciers upstream, causing them to flow faster and thin more rapidly. In Greenland, many of the fastest moving glaciers terminate in fjords, where warm Atlantic waters are intruding farther inland than ever before, accelerating their retreat. This ocean-driven melt is particularly difficult to predict and control because it depends on large-scale ocean circulation patterns that are themselves being altered by climate change. Ocean warming also affects the water beneath the ice directly. Warmer water can melt more ice at the base, increasing the volume and extent of subglacial water systems. It can change the temperature and salinity of these waters, altering their density and circulation patterns. These changes can influence where subglacial lakes form, how they drain, and how water flows beneath the glacier. They can even affect the chemistry of these environments, altering the availability of nutrients and energy sources for any potential life. For exploration, this adds yet another layer of complexity. Instruments designed for one set of conditions may encounter another. Models built on past data may no longer apply. The labyrinth we seek to explore is not just changing, it is changing in ways that are increasingly difficult to anticipate. The atmosphere, too, plays a subtler but equally significant role. As it warms, it holds more moisture, leading to changes in precipitation patterns. Some regions of the Arctic are seeing more snow, while others see less. In areas where snowfall increases, the added weight can thicken glaciers and increase pressure at their base, potentially enhancing basal melting and altering water flow. In areas with less snow, glaciers may thin more rapidly, reducing pressure and changing the dynamics in different ways. The timing of snow and melt also matters. Earlier spring melts can extend the melt season, increasing the amount of water reaching the glacier base. Late season snowfall can insulate the ice, slowing melt and affecting temperature gradients. All of these factors interact in complex ways, influencing the structure and behavior of the labyrinth beneath the ice. Another consequence of a warming climate is permafrost thaw. Much of the Arctic's land is underlain by permafrost, ground that has remained frozen for thousands of years. As it thaws, it releases water into the hydrological system, which can influence glacier flow and subglacial hydrology. Thawing permafrost can also destabilize sediments, altering the landscape beneath and around glaciers. In some cases, this can open new pathways for water flow. In others, it can block existing channels. Either way, it adds another layer of variability to an already complex system, and because permafrost thaw is accelerating as the Arctic warms, its influence on the subglacial environment is likely to grow in the coming decades. The climate's hidden hand reaches even deeper into the very structure of the ice itself. As temperatures rise, the thermal profile of glaciers changes. Warmer ice is softer and deforms more easily, increasing the rate of flow. It is also more susceptible to crevicing, allowing meltwater to penetrate deeper. This combination can lead to faster, more dynamic glacier behavior. Surges, collapses, sudden accelerations that were once rare but are becoming more common. These events can dramatically alter the labyrinth beneath the ice, rerouting water, reshaping channels, and changing the pressure and temperature conditions in which exploration must occur. They can also increase the frequency of iceberg calving and subglacial floods, adding new hazards for both natural systems and human activity. All of these changes, thinning ice, increased meltwater, warming oceans, shifting precipitation, thawing permafrost are interconnected. They amplify one another in feedback loops that accelerate the transformation of the Arctic. Thinner ice is more vulnerable to melting, which exposes darker surfaces that absorb more heat, which leads to further melting. More meltwater lubricates glacier flow, increasing the delivery of ice to the ocean, which contributes to sea level rise and alters ocean circulation, which can bring more warm water into the Arctic. These feedbacks make the system not just dynamic, but self-reinforcing, pushing it towards states that are increasingly unfamiliar and unpredictable. For those trying to explore beneath the glaciers, these changes pose profound challenges. The environment is no longer just hostile, it is unstable. Conditions that held for centuries can shift in a matter of years. Baselines that once seemed reliable are now moving targets. Equipment designed for one set of conditions may fail in another. Long-term plans may be rendered obsolete by rapid changes on the ground. And the very features we seek to study, subglacial lakes, channels, ecosystems, may disappear or transform before we can reach them. The labyrinth we are trying to map is being redrawn even as we plan our expeditions, yet this instability also offers opportunity. As glaciers thin and retreat, they expose areas that were once inaccessible. As subglacial lakes drain or connect to the surface, they offer glimpses into environments that were previously sealed away. As meltwater increases, it can carry sediments, chemicals, and even microorganisms from the base of the ice to the surface, providing indirect evidence of what lies below. These changes, while challenging, also open new windows into the hidden world beneath the Arctic. They remind us that exploration is not just about overcoming obstacles, but about adapting to new realities, and that those realities are always shifting. Perhaps most importantly, the climate's hidden hand forces us to confront the urgency of exploration. The world beneath the Arctic ice is not timeless, it is changing, and in some cases it is disappearing. Subglacial lakes that have existed for millennia may drain in a single event. Ecosystems that have evolved in isolation may be exposed and altered. Sediments that record ancient climates may be eroded or redistributed. If we wait too long, we may lose the chance to study these environments in their original state. The same warming that makes exploration more difficult also makes it more necessary. We are racing against time, and the clock is ticking faster than ever. But as much as climate complicates our efforts, it also connects them to something larger. The hidden world beneath the Arctic glaciers is not just a curiosity. It is part of the Earth's climate system, shaped by it and shaping it in turn. The ice that thins and retreats reflects less sunlight, warming the planet further. The meltwater that flows from beneath the glaciers influences ocean circulation, weather patterns, and ecosystems around the world. The sediments that emerge from beneath the ice record past climates and offer clues about future ones. To study what lies beneath the Arctic is to study the climate itself, its past, its present, and its future, and in that study, another question emerges. One that has driven much of our curiosity about these hidden realms from the beginning. If these isolated, shifting, pressurized environments beneath the ice can exist at whole, could they also harbour life? Could something be alive down there in the dark, cut off from sunlight and surface for thousands or millions of years? Deep beneath the Arctic's glaciers, far from sunlight, wind, and all the familiar rhythms of the surface, there may be worlds where life endures in ways we have barely begun to imagine. If such life exists, it is not life as we know it from forests or coral reefs or even the open ocean. It is life shaped by isolation, by darkness, by immense pressure, and by the absence of everything we think life needs. It is life that has never seen the sun, never breathed oxygen from the atmosphere, never known the changing of the seasons. It is life that whispers in the dark, sustained by forces so subtle and so alien to our everyday experience that it seems almost improbable. And yet, improbable does not mean impossible. If anything, the history of life on Earth suggests the opposite. Wherever there is water, energy, and time, life finds a way. For most of human history, we assumed life required sunlight. Plants convert light into chemical energy through photosynthesis, forming the base of nearly every food web on the planet. Animals eat plants or eat other animals that eat plants. Even the microbes that underpin many ecosystems rely indirectly on sunlight. Take that light away and life withers, or so we thought. That assumption began to unravel in 1977 when scientists exploring the Galapagos Rift discovered hydrothermal vents on the ocean floor, places where superheated water, rich in minerals, gushes from the crust. Around those vents thrived ecosystems utterly unlike anything we had seen before. Giant tube worms, clams, crabs, and countless microbes, all living in total darkness. These organisms did not rely on sunlight at all. Instead, they derived energy from chemical reactions, a process known as chemosynthesis. The microbes oxidized hydrogen sulfide and other chemicals in the vent fluids, producing energy and organic matter. Larger organisms fed on them or formed symbiotic relationships. Entire ecosystems flourished independent of the sun. And that discovery changed our understanding of life's possibilities. It showed that life does not need light, it needs energy, and energy can come from many sources. Since then, scientists have found life thriving in places once thought barren, deep within Earth's crust, inside Antarctic subglacial lakes, in acidic hot springs, in radioactive waste, and in permafrost tens of thousands of years old. Everywhere we look, life seems able to adapt, persist, and evolve in conditions that would destroy most known organisms. This remarkable resilience is why many scientists believe that if liquid water exists beneath the Arctic glaciers, and there's every reason to think it does, then life may well exist there too. What might such life look like? Almost certainly it would be microbial. The conditions beneath the ice, darkness, high pressure, low temperatures, limited nutrients, are not conducive to large, complex organisms. But microbes are astonishingly versatile. They can metabolize a wide range of chemical compounds, survive extreme conditions, and persist for millennia with minimal energy. In subglacial lakes beneath Antarctica, scientists have detected microbial life in waters sealed off from the atmosphere for hundreds of thousands of years. Some of these microbes metabolize iron or sulfur from the bedrock. Others use hydrogen produced by chemical reactions between water and rock. Some appear to feed on dissolved organic matter that has been trapped beneath the ice since long before humans existed. These ecosystems are sparse compared to surface environments. A few thousand cells per milliliter of water compared to millions in the open ocean. But they are alive nonetheless, quietly cycling nutrients and energy in the darkness. If similar ecosystems exist beneath the Arctic glaciers, they could tell us a great deal about how life adapts to isolation and extreme conditions. They might reveal new metabolic pathways, ways of extracting energy from minerals or chemical gradients that we have never seen before. They might harbour ancient lineages of microbes that diverged from their surface, relatives hundreds of thousands or millions of years ago, offering a glimpse into evolution frozen in time. They might even show us how life could persist elsewhere in the universe. The icy moons Europa and Enceladus, both believed to harbour subsurface oceans beneath thick shells of ice, present conditions not unlike those beneath Earth's glaciers. Darkness, pressure, water, and chemical energy. If life exists there, it would likely resemble the microbial ecosystems beneath our ice sheets. Studying those ecosystems on Earth is therefore not just about understanding our own planet. It is also a rehearsal for searching for life beyond it. The idea of life beneath Arctic glaciers is more than just speculation. There are tantalizing clues that something might be there. Meltwater emerging from beneath Greenland's ice sheet contains microbial communities, some of which appear to originate from subglacial environments. Sediments beneath glaciers contain organic matter that could sustain microbial metabolism. Chemical gradients, differences in concentration of substances like iron, sulfate, and hydrogen, exist in these environments and could serve as energy sources. And we know that liquid water does exist beneath many glaciers, thanks to pressure melting, geothermal heat, and friction. Combine water, energy, and time, and life's chances improve dramatically. The question is not whether life could exist there, it is whether it does, and if so, how it survives. Reaching these potential ecosystems, however, is extraordinarily difficult. The same barriers that make exploration of subglacial lakes challenging, pressure, temperature, contamination, and access, apply here as well. Drilling through kilometers of ice without introducing surface microbes is a delicate task. Even the heat from a drill can change the local environment, melting ice, altering chemical gradients, or killing sensitive organisms. Sampling water or sediment without contamination is equally challenging. Instruments must be sterilized, sealed, and capable of withstanding extreme pressure and cold. And once samples are retrieved, they must be handled carefully to preserve any microbes they contain. Even with these precautions, distinguishing indigenous organisms from contaminants can be difficult. A single microbe introduced from the surface could multiply and obscure the native community. Despite these challenges, scientists have made progress. In 2013, a US-led team successfully drilled into Lake Whillans, a subglacial lake beneath 800 meters of Antarctic ice, using a hot water drill sterilized with ultraviolet light and hydrogen peroxide. They recovered water and sediment samples that contained active microbial communities. These microbes were metabolizing iron, sulfur, and nitrogen compounds, evidence of a functioning ecosystem sealed away from the sun. Similar results have come from other Antarctic lakes and from sediments beneath Greenland's ice. Each discovery strengthens the case that subglacial ecosystems are not rare exceptions, but widespread features of icy environments. If they exist beneath the Arctic glaciers, they could number in the trillions, forming a hidden biosphere beneath the ice. The implications of such a biosphere are profound. For one, it would expand our understanding of the limits of life. We already know that life can survive without sunlight, but subglacial ecosystems push that resilience even further. They show that life can persist in isolation for hundreds of thousands of years, sustained only by the slow trickle of chemical energy from rock and water. They suggest that life is not fragile and rare, but robust and adaptable, capable of thriving in conditions that seem inhospitable. That has implications for our search for life elsewhere. If microbes can survive beneath kilometers of ice on Earth, they might survive beneath the ice of Europa or Enceladus. They might even persist in the subsurface of Mars, where liquid water could exist deep underground. Such discoveries would also change how we think about Earth itself. Subglacial ecosystems, though hidden and sparse, are part of the planet's biosphere. They contribute to biogeochemical cycles, transforming minerals, recycling nutrients, and perhaps even influencing the chemistry of meltwater that eventually reaches the ocean. They are time capsules, preserving lineages and metabolic strategies from Earth's distant past. They are laboratories showing us how life responds to isolation, scarcity, and pressure. And they are reminders that life is not confined to the places we find comfortable. It exists wherever it can, and sometimes where we least expect it. But life beneath the ice, if it exists, is also vulnerable. Its isolation is both its defining feature and its greatest protection. A single drilling operation could introduce foreign microbes that outcompete or disrupt native species. A small change in temperature or chemistry could alter the balance that has sustained life for millennia. Even the act of exposing these environments to light and air could have consequences we do not yet understand. That is why scientists approach subglacial exploration with such caution. They know that they are not just searching for life. They're intruding into ecosystems that have never encountered us before. They must tread lightly, balancing the desire to know with the responsibility to protect. There is also the possibility that life beneath the ice is not thriving, but dormant. In such extreme conditions, microbes might spend most of their existence in a state of suspended animation, metabolizing so slowly that their generation times are measured in centuries. They might survive on trace amounts of energy, dividing once in a human lifetime or less. They might be relics from a time when the environment was different, clinging to existence as the world around them changed. If so, studying them could reveal not just how life survives, but how it endures, how it waits out hostile conditions and persists across geological timescales. It could show us that life's story is not just about flourishing, but about enduring. even in silence. In the end, the search for life beneath the Arctic glaciers is about more than microbes. It is about our desire to understand what life is and where it can exist. It is about testing the boundaries of biology and expanding the definition of habitability. It is about connecting Earth's hidden biospheres to the search for life elsewhere in the universe. And it is about humility, the recognition that our planet still holds mysteries we have not solved, that there are still places untouched by human eyes, and that life may be thriving there without our knowledge. If we find life beneath the Arctic ice, it will change how we see our planet. It will remind us that Earth is still full of surprises, that its story is far from fully told. It will suggest that life is not a rare accident, but a natural consequence of the right conditions, emerging wherever water, energy, and time converge. And if we do not find life, that too will teach us something about the limits of biology, the fragility of ecosystems, and the uniqueness of the surface world we inhabit. Either way, the search itself matters. It pushes our technology, our science, and our imagination to new frontiers. It connects disciplines, glaciology, microbiology, chemistry, planetary science, into a shared quest. It turns the hidden depths of our own planet into a proving ground for future missions beyond it. And it transforms the Arctic from a frozen barrier into a place of possibility, where whispers of life in the dark may yet become voices. Far beneath the Arctic's glaciers, in those lightless realms where pressure crushes rock and water flows unseen, there is more than just the story of Earth. There is a reflection of something larger, a mirror held up to the cosmos. For all their remoteness, the hidden lakes, channels, and possible ecosystems beneath our polar ice sheets are not unique. The conditions that shape them, the cold, the darkness, the pressure, the isolation, the chemical gradients that sustain life without sunlight, are not confined to this planet. They exist elsewhere, scattered across our solar system and beyond. On worlds where ice hides oceans, where liquid water flows beneath frozen crusts, and where life, if it exists, must adapt to the same kinds of challenges that life would face beneath the Arctic's glaciers. In studying these hidden realms here on Earth, we are not just probing our own planet's secrets. We are rehearsing for exploration elsewhere, learning how to reach, understand, and protect environments that may hold answers to one of humanity's oldest questions. Are we alone? The most obvious of these extraterrestrial mirrors is Europa, one of Jupiter's 4 large Galilean moons. Slightly smaller than our own moon, Europa is a world of ice and rock, its surface etched with cracks and ridges that betray the movement of ice over liquid water. Beneath that surface, beneath ice estimated to be 10 to 30 kilometers thick, lies a global ocean containing more water than all of Earth's oceans combined. That ocean is kept liquid not by sunlight, but by tidal heating, the result of Jupiter's immense gravity flexing and kneading Europa's interior as it orbits. The result is a world with a vast, dark, pressurized ocean sealed beneath ice, an environment strikingly similar to the subglacial lakes and channels beneath Earth's glaciers. If life exists there, it would likely resemble the microbial ecosystems we think might exist beneath our own ice sheets, living off chemical energy from the interaction of water and rock, or from compounds delivered through cracks in the ice. Enceladus, a small moon of Saturn, offers another mirror. Beneath its bright icy surface lies a global ocean as well, kept liquid by the same tidal forces that warm Europa. Unlike Europa, however, Enceladus gives us direct evidence of that ocean's existence. Through fractures near its south pole, it sprays plumes of water vapor, ice particles, and organic molecules into space. Material that spacecraft like Cassini have flown through and sampled. Those plumes contain salts, simple organic compounds, and tiny grains of silica, all signs of chemical interactions between water and rock on the seafloor. They hint at hydrothermal activity, the same kind of activity that sustains life around Earth's deep-sea vents and might sustain it beneath our ice sheets. If microbial life exists in Enceladus's ocean, it may be chemically and structurally similar to the life that could exist beneath Arctic glaciers. And if we ever send a probe into that ocean, it will face many of the same challenges as a mission to Earth's subglacial lakes, penetrating thick ice, avoiding contamination, and surviving in a dark, pressurized environment. Even farther afield, other icy worlds beckon. Ganymede and Callisto, Jupiter's other large moons, are believed to harbour subsurface oceans. Titan, Saturn's largest moon, has a thick shell of ice, overlying a deep ocean of water and ammonia. Pluto, once thought too small and cold to host liquid water, may have a subsurface ocean as well. And beyond our solar system, exoplanets and exomoons, orbiting distant stars, may host similar environments, though we cannot yet see them directly. All of these worlds share key features with the hidden realms beneath Earth's glaciers: thick ice, liquid water beneath, chemical energy sources, and long-term isolation from sunlight. They are variations on a theme, and that theme suggests something profound. The conditions that make life possible beneath ice are not rare. They may be among the most common habitable environments in the universe. This realization has transformed how scientists think about the search for life beyond Earth. For much of the 20th century, that search focused on planets with surface conditions similar to ours, warm, temperate worlds where liquid water could exist in lakes, rivers, and oceans under an atmosphere and sunlight. Mars, once wetter and warmer than it is today, was the prime target. Venus, before we understood its runaway greenhouse effect, was another. Even distant exoplanets are often judged by whether they lie in the habitable zone, the region around a star where liquid water could exist on the surface. But the discoveries of subsurface oceans on icy moons and the realization that life can thrive without sunlight have expanded that perspective. Habitability is not limited to the surface. It may be far more common beneath ice, shielded from harsh radiation and insulated against extreme temperatures. In this new vision of habitability, Earth's subglacial environments are invaluable analogues. They give us natural laboratories for studying how water interacts with rock in the absence of sunlight, how chemical energy can sustain ecosystems, how life adapts to pressure and isolation, and how microbial communities evolve in sealed environments over long timescales. They allow us to test technologies and techniques that could one day be used on other worlds. Drills that can penetrate thick ice without contamination, autonomous probes that can operate in dark, pressurized water, sensors that can detect chemical signatures of life in hostile conditions. Every mission to a subglacial lake, every experiment beneath a glacier is not just an exploration of Earth, it's a dress rehearsal for Europa, Enceladus, and worlds beyond. This connection works both ways. The discoveries we make on other worlds also inform how we think about Earth's hidden environments. Cassini's detection of organic molecules in Enceladus's plumes, for example, highlights the importance of water-rock interactions as potential energy sources for life, interactions that likely occur beneath Earth's glaciers as well. Models of Europa's ocean circulation help scientists understand how water might move beneath ice sheets on Earth, and the search for biosignatures, chemical, isotopic, or structural traces of life on other worlds pushes us to refine our methods for detecting them here. It teaches us to look for subtle signals in complex data, to distinguish between biological and non-biological processes, and to interpret evidence cautiously but creatively. The parallels between Earth's subglacial environments and extraterrestrial oceans also raise intriguing questions about life's origins. Some scientists believe that life on Earth may have begun not in shallow, sunlit seas, but around hydrothermal vents on the ocean floor. Environments rich in chemical energy, shielded from harmful radiation, and conducive to the formation of complex organic molecules. If life can begin in such places, then it might also arise beneath ice, where similar conditions exist. That possibility blurs the line between Earth-like and alien environments. It suggests that the distinction between the Arctic's hidden lakes and Europa's ocean may be one of degree, not kind, and it implies that by studying life beneath our own ice sheets, we may be glimpsing how life could emerge elsewhere, and perhaps how it first emerged here. this cosmic mirror also challenges how we think about exploration itself. Sending a probe through kilometers of ice on Earth is hard enough. Doing so on Europa or Enceladus, tens or hundreds of millions of kilometers away, is orders of magnitude harder. Communication delays make real-time control impossible. Power sources must be compact, reliable, and long-lasting. Instruments must survive years of travel through space before operating flawlessly in an alien environment. Sterilization is even more critical, because contaminating another world with Earth microbes could destroy the very evidence we seek, and yet the basic principles are the same. A cryobot melting through Europa's ice will face many of the same challenges as one descending into a subglacial lake beneath Greenland. An autonomous underwater vehicle exploring Enceladus's ocean will rely on the same navigation and sensing technologies as one operating beneath an Antarctic ice shelf. Earth's glaciers are proving grounds, places where we can practice for the far more difficult missions to come. There is a poetic symmetry in this. The same environments that frustrate us here, the darkness, the pressure, the moving ice, the risk of contamination, are the very environments that may hold life elsewhere. The same problems we must solve to reach subglacial lakes are the ones we must solve to explore alien oceans, and the same questions we ask of the Arctic's hidden biospheres. How do they survive? What fuels them? How do they evolve? Are the questions we will ask on Europa, Enceladus, and beyond. In this way, Earth's most inaccessible environments become keys to the universe. They show us not just what is possible here, but what may be possible everywhere. This perspective also reframes our relationship with the Arctic. It is not just a remote, inhospitable region at the edge of the map. It is a bridge between worlds, a place where planetary science, biology, geology, and engineering converge. It is where questions about life on distant moons become questions about life on Earth, and where answers about Earth feed back into our search for life elsewhere. The Arctic's hidden realms remind us that exploration is not a straight line outward into space, but a loop, a dialogue between the near and the far, the known and the unknown. What we learn beneath our own glaciers shapes how we search beyond them, and what we find beyond them shapes how we look beneath our own. It is possible that when we finally penetrate the ice of Europa, or sample the plumes of Enceladus, we will find no life there. It is also possible that we will find something astonishing. Microbes swimming in darkness, drawing energy from rocks and minerals as their cousins may be doing beneath Earth's ice. Either outcome will teach us something fundamental about the universe. If life is absent, it will show us that the conditions beneath ice, while potentially habitable, are not always inhabited. If life is present, it will suggest that biology is not a rare accident, but a common outcome of the right conditions. Either way, the work we do beneath Earth's glaciers will have prepared us to understand what we find, and perhaps that is the greatest lesson the Arctic's hidden world offers us. That our planet is not isolated, its mystery is not unique. The same physics, chemistry, and potential for life that shape our subglacial environments are at work across the cosmos. The same stories unfolding beneath Greenland's ice are unfolding beneath the ice of distant moons. The Arctic is not just a place, it is a model, a microcosm, a mirror in which we glimpse other worlds. And in that mirror, we also glimpse ourselves, a species reaching outward, driven by curiosity, trying to understand not just where we are, but where we might go. Even if one day we conquer the engineering challenges, master the physics, and build machines that can slip through the labyrinth beneath the Arctic glaciers as easily as a fish glides through water, there will still be a part of that world that we cannot and perhaps should not reach. Because beneath the ice, past the pressure and the darkness, past the rivers we cannot see, and the lakes we cannot touch, lies not just a physical frontier, but a philosophical one. It is the realization that some mysteries are not meant to be solved completely, that some questions must remain partly unanswered if they are to retain their meaning. And this is perhaps the deepest truth about the hidden world beneath the North Pole's glaciers. It's not only a place we cannot fully explore, it is a place that, in some profound sense, we should never fully conquer. We are, by nature, a species that wants to know. Curiosity has driven every leap we've made, from the first tools to the first telescopes, from crossing oceans to walking on the moon. It has built civilizations and reshaped continents. It has sent machines to the edge of the solar system and uncovered the structure of DNA. And it is the same curiosity that pulls us northward, into the cold and the dark, to ask what lies beneath the ice. We want to know what worlds exist beneath kilometers of frozen water. We want to know if life is there, how it survives, what it can teach us about ourselves and the universe. But curiosity, powerful as it is not the same as entitlement. Wanting to know does not mean we are meant to know everything. The line between exploration and intrusion is thinner than we like to admit. And beneath the Arctic glaciers, that line matters more than ever. For the ecosystems that may exist down there, if they exist at all, isolation is everything. They have evolved, or persisted, or endured without interference from the surface for thousands or even millions of years. Their chemistry, their balance, their very existence depends on that isolation. To breach it, even with the best of intentions, is to risk destroying what makes them unique. A single bacterium introduced by a drill bit could outcompete native microbes that have never encountered such an arrival. A small change in temperature from the heat of our instruments could shift the chemistry of an entire ecosystem. A drop of drilling fluid could contaminate a pristine environment beyond recovery. These are not hypothetical concerns. They are real risks, documented in every attempt to explore subglacial lakes and channels, and they force us to confront an uncomfortable question. Is knowledge always worth the cost? There is also the question of authenticity. A sealed subglacial lake is a time capsule, a record of conditions that may date back hundreds of thousands of years. It contains not just water and sediment, but information about past climates, about geological processes, about the evolution of life. Once we open it, we change it. Even if we are careful, even if we avoid contamination, the act of breaching that isolation alters pressure, temperature, and chemistry in ways that cannot be undone. It is like opening a tomb. Once the seal is broken, the contents are never quite the same. If we want to study these environments as they truly are, not as they become after we touch them, then we must accept that some part of them must remain beyond our reach. This tension between our desire to know and the need to protect what we seek to know is not unique to the Arctic. It is present wherever exploration pushes into untouched realms. It was there when we first sent probes to Mars, forcing us to grapple with planetary protection protocols to avoid contaminating a potentially habitable world. It is there in the plans to drill into Europa's ice, where any contamination could compromise the search for life. And it is there beneath our own glaciers, where the environments we wish to study may be irreversibly altered by the very act of studying them. These are not reasons to stop exploring, but they are reasons to proceed with humility, restraint, and a willingness to leave some mysteries partially intact. Humility is not a trait our species has always embraced. We like to think of the world as something to be mapped, measured, and mastered. We celebrate the moment we plant a flag, take a sample, or bring back a photograph. We mark progress in terms of what we have claimed. But beneath the Arctic glaciers, mastery is an illusion. The forces at work there, pressure, gravity, time, are older and stronger than anything we can build. The labyrinth beneath the ice is constantly reshaping itself, beyond our control. The possible ecosystems within it have evolved independently of us, beyond our influence. The best we can do is approach as guests, careful, temporary, aware that we're entering a place that does not belong to us. There is value, too, in not knowing everything. Mystery has always been part of what drives us, but it is also part of what grounds us. It reminds us that the universe is larger and stranger than we are. It keeps us humble, curious, and cautious. It teaches us that our understanding will always be partial, that there will always be horizons beyond our reach. The hidden world beneath the Arctic's ice is one of those horizons. It is a reminder that even on a planet we have mapped and measured, there are still places untouched, still stories untold, still questions unanswered. That is not a failure, it is a feature of a living, changing world, and of our relationship with it. And perhaps, in a deeper sense, the mystery must remain, because it tells us something fundamental about life itself. Life thrives not just in the places we can see and measure, but also in the places that remain hidden. It is not confined to the obvious or the accessible. It persists in darkness, under pressure, in silence beyond our reach. That persistence is part of what makes life extraordinary, and part of what makes our planet extraordinary. If we were to pierce every glacier, drain every lake, and expose every hidden ecosystem, we might learn much, but we might also lose something precious. The knowledge that there are still corners of the Earth where life, if it exists, does so entirely on its own terms. The Arctic itself seems to insist on this. Every time we get close to revealing its deepest secrets, it changes. Channels close, lakes drain, ice shifts, instruments are lost, missions fail. It is as if the labyrinth moves not just because of physics, but because the mystery itself resists us, demanding patience, caution, and respect. That resistance is frustrating, but it is also instructive. It reminds us that exploration is not conquest. It is a relationship, a dialogue between what we want to know and what the world is willing to reveal. And like any relationship, it depends on trust, patience, and boundaries. This perspective does not diminish the importance of exploration. On the contrary, it enriches it. It suggests that our goal is not to strip away every layer of mystery, but to understand the world more deeply while leaving parts of it intact. It suggests that discovery is not always about possession, but sometimes about reverence. It suggests that the unknown is not a void to be filled, but a presence to be acknowledged. Beneath the Arctic glaciers, that presence is palpable. It is in the darkness that swallows light. It is in the pressure that bends steel. It is in the water that moves unseen, and the life that may or may not exist. It is in the knowledge that no matter how far we go, there will always be something beyond. And perhaps that is the point. The hidden world beneath the Arctic ice is not a puzzle to be solved once and for all. It is a conversation, one that will unfold over decades, centuries, and beyond. Each generation will push a little farther, learn a little more, and leave a little more mystery intact for those who come after. We will build better machines, refine our models, deepen our understanding. We will make mistakes, lose instruments, and learn from failure. And through it all, the labyrinth will continue to move, the water will continue to flow, and the darkness will continue to hold its secrets. In the end, the greatest gift the Arctic's hidden world may offer us is not its answers, but its questions. It asks us who we are when faced with the unknown. It asks us how much we are willing to risk for knowledge, and how much we're willing to leave untouched. It asks us whether we can be explorers without being conquerors, whether we can learn without destroying, whether we can honour what we do not understand. These are not easy questions, but they are the questions that matter, not just beneath the ice, but everywhere we seek to explore. And so, as we look northward toward the glaciers, the darkness, and the mysteries beneath them, we are reminded that exploration is not just about going farther, it is about going deeper. In every sense, it is about understanding our place in a world that will always exceed our grasp. It is about accepting that some mysteries are meant to remain. The Arctic's hidden world is one of those mysteries. It resists us, humbles us, inspires us. It challenges our ingenuity and tests our resolve. It reveals pieces of itself, then slips away again, leaving us to wonder, to imagine, to dream. That dream, the dream of what lies beneath, of what might live in the darkness, of what secrets the ice still holds, is perhaps more powerful than any discovery we could make. It keeps us reaching, questioning, striving. It reminds us that there is always more to learn, always more to seek, always more beyond the horizon. And in that sense, the mystery beneath the Arctic glaciers must remain. Not as a barrier, but as a beacon. Not as a limit, but as an invitation. Not as a failure of exploration, but as its truest expression. Because some questions are not meant to be answered, they are meant to be lived with, to remind us of what we don't know, to keep us curious, to keep us humble, to keep us reaching into the darkness, not to conquer it, but to understand that the darkness itself is part of the story, part of what makes our world strange and beautiful and worth protecting. And as you drift off now, as these words fade into the background and sleep begins to pull you under, carry this with you, that somewhere beneath the ice at the top of the world, there is a place we cannot reach, a darkness we cannot pierce, a mystery we cannot solve. And that is exactly as it should be, because the Earth still has secrets, and the sum of those secrets are meant to remain hidden, not forever, but for now, waiting, patient, enduring, in the cold, in the dark, in the silence, where the ice holds its breath, and the water flows unseen, and the mystery remains.